Good afternoon. Welcome to today's webinar with SCA. Bob Barbet will be sharing with us his insights on integrating petrophysics with rock properties and production data due to organic shale well performance. And before we start today's webinar, we're going to remind you that you are being muted during the presentation, but you can ask questions using the question feature in your GoToWebinar dashboard. We'll cover those questions at the end of the presentation. Bob Barbet started his career with Schlumberger and worked in various asset groups and teams with hydraulic fracturing for the first 10 years of his career, and he's been consulting on petrophysics and completion optimization since then. He has served on as a SP Distinguished Lecturer, and his topic is integrating petrophysics with hydraulic fracturing treatments and optimizing the process. And he's used that integration process in a wide variety of reservoirs throughout North America, conducting field studies for a number of operators, focusing on effective frac length, recovery factor, and providing best practices. Bob is responsible for petrophysical analysis in major fields worldwide, and he's done integrated reservoir characterization studies identifying those remaining mobile hydrocarbons. He's authored over 36 papers in this integrations of petrophysics with completion designs, horizontal wells, and reservoir characterization. He has a bachelor's from the Naval Academy and MBA from University of Florida. He's a member of SPE, SPAA, and APG. Bob teaches a class for SCA with the same title, Integrating Petrophysics with Rock Properties and Production Data. That class will be offered in Houston in February. And here's information where you can sign up to attend that class. You can contact SCA by phone or by email. And of course, we can offer these classes in-house as well. And we'd like to remind you that this is our last webinar for the month of December, but starting in January, we'll continue our webinar series. We have Roshkan Shoshki on January 11th, Oscar Lopez-Gamundi on January 18th. On January 25th, we'll be joined by Leo Roldhart and Garrett Knitters. On January 31st, John Lorenz and Scott Cooper. All of these SCA instructors will be speaking on their topics of expertise. And SCA, of course, in addition to training, we offer consulting, direct hire services, and projects and studies. So before we start our webinar today, I'd like to run a couple of polls on the audience. And so I'm going to launch the first poll. And this is a chance for you to participate, to vote. Tell us what's your primary discipline. We'd like to see who we have attending the webinar today so that Bob can make sure it is directed towards the audience. So we've got 3/4 of you have voted so far. Looks like the votes are coming in pretty quickly. We almost have everyone, so I'll go ahead and display these results. So it looks like the majority of you are geoscientists, followed closely by petroleum engineers, and we have a few petrophysicists in the crowd. So our next poll is how many years of full-time experience do you have in the industry? And so again, here's a chance to see who our audience is and make sure we understand the perspectives of the various attendees. We're getting a pretty quick response here, and it looks like we've got a great distribution over a number of different experience levels. Almost everyone has voted, so I'll go ahead and close the poll and share these results. It looks like it's a bimodal distribution with a larger group with 11 to 20 years and over 30 years. So thanks for that information. And so I'm going to give the presentation rights over to Bob. And again, I'll remind you that you'll be muted during the presentation, so you're welcome to post questions as we go through Bob's presentation, and we'll try to handle some of those questions at the end today. Bob, it's over to you. Thanks.
Thank you, Susan. my screen going here. Trying to kill this guy. Down. Where's he? Okay. Get him out of the way there. All right. Okay, thanks for joining us today. I'm certainly honored to be part of this series. This is the 8th in the series of webinars on the courses that SCA offers. And we were doing a dry run on Monday, and Susan asked me, hey, what she thinks is driving the high attendance. The attendance was about 2x what they saw on some of the other webinars. And I said, well, it's based on the group I'm working with here. It's some of the top experts in the world and subject matter experts in these disciplines. So when I first heard that, I was invited to join this group. A line from one of my famous mentors came to bear. Let me page down here. There goes the neighborhood. So to answer your question, Susan, I think it was the subject matter and not the instructor. But we're in a pretty august group there. But at any rate, a little bit more on my background. Susan covered the high points there, and kind of what got us into this is we started out working optimizing fracs with log data and taught a number of schools from 1992 on. Around 2010, started working in organic shale reservoirs in the U.S. And pretty much all the stuff we're doing right now follows the workflow that we're going to discuss in this webinar here. Specific to where we've worked, we've done over 1,200 wells in the Permian Basin, Midland Basin, Delaware Basin, also, pretty much all over Marcellus, Utica, Eagle Ford, Bakken, Powder, DJ, Mid-Continent. So it's the techniques we're talking about here. Most of the examples we have are from the Wolfcamp and the Permian, since we've done the majority of our work there. But again, the principles are applicable pretty much everywhere. So it's not something that's just specific to the Permian, but again, that's where we've done most of the work. What we'd like to do is kind of get everybody up to speed on how do you get an idea of what the well's going to make? How do you predict well performance ahead of time? You may not always have wells right next door to you to look at. You may not always have type curves. You may be in a new area. So how do you take what you have as far as log data and production data, tie that together, and put it together to try and predict what performance is going to be?
So Bob, I'm going to interrupt you. We're going to ask another poll question. So this is really talking about what sorts of what is your company using to estimate EURs for your organic shale wells? And so let's see if we get some responses from the attendees here. We're getting quite a few in the ARPS category and quite a few in the other category. So the votes are coming in. All right, we're still getting quite a few in the other category. So I'm going to go ahead and close the poll at this point. Most of you have voted and share the results, and it looks like quite a few in the other category as opposed to using ARPS or some of the other methods listed as well.
That was question one.
I'll hide that. Yep, and then I will ask the question about what organic shale play areas are you currently working in. And so again, we have a list of several basins that are available here, getting good response. Quite a few in the other category, but looks like Permian Basin is leading the charge here. So most of you have voted, so I'll go ahead and close that poll and share it with the respondents. 43% in the Permian, and followed by the other basins. All right.
Sounds good. All right. So how do you predict organic shale well EURs? What's the first thing you do? Well, most people look, what's the offset's doing? What's the nearby offset wells doing? You also have type curves you can develop for various areas from multiple wells. Some of the issues that come up there is what if you had an earlier generation frac on those wells and you're going to be able to use a more modern Gen 3 frac on the new ones? How's that going to affect it? The other thing is some of these laterals are getting longer and longer. You're going out 2 miles away from the vertical pilot well, and do your landing zone and stress barrier relationships stay the same, or do they stay the same as where your offset producer is the bigger question, because your offset producer could be several miles away. So it's not so much between the pilot and the tow that you're worried about, but do you have changes there? Because you can definitely change the character of your performance by going above or below stress barriers. And the last one's where we're doing most of our work to date is, what if you don't have any offset producers directly in the area? What do you do then? With petrophysics, what we typically do on these projects for larger operators is we come up with a deliverable of millions of barrels of oil per section, and it's typically for the entire horizon, like Wolfcamp A, Wolfcamp B, etc. And then you'll give them an aggregate number, and then the operators will typically slice and dice that depending on how many laterals they want to put in there and all that. The producing height, oil in place, I think is more relevant in that bench OIP, because typically in most areas you don't produce the entire bench based on what our assumptions and our modeling. But what we like to see is, producing height of a propped height plus unpropped height. And we'll talk a little bit about how we get the unpropped height, because that's definitely the biggest moving part in this thing as far as that goes. Your porosity, your saturations, your net pay, those are a little more straightforward. You've got some solid numbers to work with, not so much on the propped height or the producing height. But we'll talk about that coming up. But the beauty of this is once you've got a consistent recovery factors, once you've got consistent assumptions, and once you've got a consistent model, you can go through here and predict your performance prior to completion, and on the bench mount, bench by bench or well by well, and determine how many benches you can develop and determine what you're going to make out of the entire system. And again, the big benefit is it doesn't require offset production in the immediate area. You got to have it in the basin, but not in the immediate area. You have to have it in similar rock types in the area, but that's the only thing that's the only caveat on that. What are you historically? What have we done? What's that?
Bob, I'm going to interrupt you one more time and ask one more polling question about petrophysical analysis methods.
Okay.
And so we're going to ask the group to vote as to which current petrophysical analysis method you're using. And we're getting some responses now. Looks like many of you are using commercial packages in-house. Looks like a few people are using spreadsheets, and we've got a variety of responses here.
Okay.
So most of you have voted, so I'm going to go ahead and close and share the results. 49% are using a commercial package in-house, followed by consultants with commercial packages.
Okay, sounds about right. Good. Excellent. Well, typically what we've done in the past, for the logging schools, you run some type of multi-mineral model. You definitely can't just run a straight RGV clay model like you do in conventional rocks, a lot of conventional rocks. It's a little more complicated. You got a lot more moving parts in there, but typically a multi-mineral model like the ELAN type model, all the service companies have those statistical type models. Try to estimate the percentage of each component, and then matrix density from mineral composition, then go back and get a density from the matrix density. Typically you have to have a full suite of logs. And in the past, you can stretch it to somewhat, but usually one input per output is pretty stable. So you probably need a PE curve and everything along with the regular triple combo, even maybe a sonic log to define all the minerals that you need to define. Anyway, and then you have to have core data, which is pretty much the same for everything. Both methods have to use core data to give your volume percentage of the minerals. And then you have to know the rock properties of the individual components, which for your main ones, your calcite, quartz, things like that, are pretty well documented. One thing that's not well documented is your kerogen content, your kerogen volume, and your kerogen properties. In the liquids-rich shales, one of the problems is your kerogen, your TOC is where you get your kerogen. Your TOC is not just kerogen; it's also your S1 component. So you can make this method work, but typically what we've seen, particularly when we're working for like joint interest operators and aren't the operator, that are just partners in wells, and then you're comparing your numbers to the larger companies out there, that quite often you've got to make adjustments, empirical adjustments to your model to because a lot of times your answer doesn't come out exactly what the core is, so you got to make some changes to your mineral content that's not always based on measured values. So that's somewhat of a drawback. And it's not a bad way to do it. I'm not saying to stop doing it that way. It's that method works fine. The ELAN type works fairly good. It's just if you can come by with a much simpler method that's a little more efficient and gets around a lot of the unknowns here, that's what we're recommending. And it's also, I think, a lot faster as well. What we do start with, normalization is very important. I'm surprised working on some of these big projects, again, primarily for partners of larger operators. How normalization is not really stressed in a lot of these areas. We think it's critical. You can have small porosity errors are magnified by your large H's that you have. What we like to see is a triple combo. PE is good. For your oil in place, you really don't need the PE, but for your rock properties, it's really helpful as far as Poisson's ratio and stress and the Young's modulus, things like that. PE is very helpful. Sometimes you can generate a synthetic PE as well, so it's good. And the synthetic, we talk about synthetic. It's really all the stuff we're talking about in terms of synthetic is a CGG power log synthetic curve generator. Very powerful model. When I was at the Bureau of Economic Geology, we did a lot of work with neural nets, and the guy that invented the neural net for Schlumberger, I ran into him a few years back, and he says he stopped using the neural nets, even though he wrote one, and is now using the power log synthetic curve generator. So, and we basically that's a good vote of confidence. We found it's pretty stable. And it's got a lot of advantages, and we'll talk about that. What's nice is you can make equations with it and basically provide it to your operator clients, and they can use it in Excel or wherever, in a hand calculator if you want to. It doesn't require, like with neural nets, we had to have another neural net package on the user's computer to use it, where here you don't. First thing we do is we normalize the spectral gamma ray. We always like to have a spectral gamma ray somewhere in the field. Just has to be one, maybe two, but usually it's one. Normalize that similar to the PHIE RT porosity overlay. Find a shale that doesn't have any organics or very limited organics, like your Wolfcamp C, lower Wolfcamp C in the Midland Basin. Then from that point, once you have a normalized spectral gamma ray, we develop a synthetic spectral gamma ray using the conductivity, neutron, in the raw gamma ray, and that way you've got a spectral gamma ray to use on all your wells, which is nice to flag your organics and also using your calculations. VCLAY, we try to tie that back to XRD. ECS is really nice, the pulse neutron type tool, because it gives you continuous numbers. And then basically what we use there typically is grain density, the spectral gamma ray, CGR SYN, the neutron porosity, and conductivity. Again, all your curves normalize. Your density, neutron, and gamma ray normalize. Those are the ones we normalize. You notice conductivity is in there quite a bit. Conductivity is there because of the importance of the kerogen input. Try to resolve the effect of kerogen, and the PHIE method with the porosity and resistivity overlay. That's typically resistivity is an input, and conductivity is basically the same as resistivity. So that's why we include that in a lot of our measurements. Here's an example for normalization. Let me get my mouse pointer here. There we go. It's a Wolfcamp C zone. You can see the gamma ray average, neutron average, rho B average. We try to pick a zone right above the clines where we usually use it in the Midland Basin. A well-developed shale with very little organics. You see there's no crossover here. You're starting to see the crossover between the spectral gamma ray and the gamma ray down here at the top of the cline, where the organics are, and your resistivity goes up. You can see your neutron is right along the average. Your density is right along the average there. So, and if it's not along the average when you start with, which most of the time it's not, there's usually slight changes that are made on these on a lot of cases. And we've seen it, basically make a change where your well is going to make it versus the well not going to make it. So it's very important to have the normalization, and it's fairly simple. Now, if you don't have this particular marker, like your control well doesn't go down through there, typically you need to find one nearby and then just go up hole and look at some of the other members that have low kerogen and see how it compares. Analysis itself, typically we run a conventional effective porosity model with density and VCLAY, correct for VCLAY. For your matrix density, we use the mineral density just for our first pass, but again, it's in the organics, it's going to be overwritten by the equation that's tied to core. So we got two different models running. Just run Archie, use your BV hydrocarbon data to try and back that up. We'll talk about that coming up next. Your porosity is constrained by core. If you have very low V clay, your core porosity should be fairly close to your log. If you got higher V clay, there's more of a spread. That's something we're working on to make that a little more scientific, a little more analytical. But right now, we just use it as a guideline. But in no case should your porosity be higher than your core porosity. It's an upper limit. And basically run the model and say, okay, use density, V clay, conductivity, PEF if you have it. You don't really need it. And come up with a porosity measurement that matches your core. And what it does is it develops an equation that you can use to come up with that. And then what we found fortuitously, and we were concerned about this when we started, that we have to do zoning and just organic for one part and inorganic for others, intergranular for others. But we found that typically the lowest of the two is correct. So that was good. And net pay cutoff, we try to weight the percentage of organic porosity and inorganic porosity or intergranular porosity. For instance, Ingrain did a study in the Wolfcamp where they showed in 1,400 cores that 40-some% of the porosity is organic, which has a BVI of 0, both primary reducible 0, and then your matrix rocks either 4 or 5, depending on whether it's calcite based or plastic. So you use a composite of about 3% on that for the Wolfcamp. Here's an example of your BV hydrocarbon. It's kind of an independent water saturation measurement. This is actually from the Utica, but you're going to hear that when your porosity goes, basically your hydrocarbons go away at about 3% porosity. That gives you a good cutoff for your bulk volume irreducible, and also it's a good means for water saturation. If you're not making much water, or if the water's coming out of zones other than what's in the pay zones there, basically you ought to have 3% BVW. If you got 6% water, 6% porosity, that gives you 50% water saturation. We did a whole project in the Marcellus where we didn't do any water saturation calculations. We just used the BVI, which was 0.24 or something like that, and divided that by the porosity to come up with our water saturations. But, kind of a handy tool. Here's an example of the analysis. You can see over here in the left-hand track the spectral gamma ray versus regular gamma ray. This is your X-ray diffraction points, volume points, water saturations, your porosity here. You can see a pretty big spread between your density porosity and the core porosity, and that's basically from the fact of kerogen. When you run the synthetic model and you run the normal model and take the lower of the two, you can see the tie over here in the right-hand track there. So we think that's a fairly decent tie on that. Next part, we look to try and estimate the propped height. And we run a rock properties analysis using the standard Eaton equation with the dipole sonic data. Typically, we'll correlate the dipole back to triple combo data and use that because it takes out a lot of the, you can use the quality control dipole data and get regressions there rather than trying to use the actual. Using the actual dipole data is problematic sometimes because you can have spikes in the data that's not a function of the rock, it's more a function of the tool because it can't really read defined beds less than 8 feet thick in theory. You might get something that looks like a barrier that really is not. So we try to use both, integrate both of them, and come up with a final Poisson's ratio that's a function of the measured and the empirical to smooth those out. And the assumption is that the proppant's going to bench on a stress layer below the lateral, and then you take the producing height, you basically take the propped height, which is fairly well documented. We'll show you some examples of that, and then tack whatever you think is the producing height on top of that, and we'll show you where we're getting that. We come out with about 200 feet plus or minus in the Permian, and provided there's no significant stress layers above the lateral within the 200-foot interval. You can certainly limit it with that. Here's an example from the southern Midland Basin where they landed below a lateral. They were trying to target, looks like the Wolfcamp A is the red part there. They actually landed it down below the barrier and basically weren't able to access the pay on that particular well. The frac went down away from it. So the stress barrier location is fairly important to all of this, both to where your proppant starts out, because that's where your base of your producing interval should be, and also whether or not you're going to cover the entire 200 feet, which is what we're seeing if you don't have major stress barriers within the net pay interval. Here's an example from a vertical pilot well, and to come up with a producing height, we basically did about 50% of the volume for a stage frac into a single cluster in a vertical well. Ran in tracers both in the slick water portion of the hybrid and then the tail end borate part of the hybrid. Borate's in red, the slick water's in yellow. You can see basically the propped height's the same. You can get propped height in a shale well just by running the slick water model to come up with what your height's going to be, because your closure time of basically 2 days versus 3 days versus your your break time of 2 hours creates quite a disconnect there. You can see, though, which is kind of interesting, the proppant did make it all the way to the top here, both the 100 mesh here and the 2040 made it up here, but nothing really in between. The temperature log shows about 190 feet of fluid height, and you're showing about 55 feet of propped height down at the bottom, which is fairly consistent with, you can run pretty much any frac model and it'll give you fairly similar numbers. So basically you can model your proppant height by where your stress bench is and add 50 to 60 feet. So and that basically suggests that about 75% or 75 to 75% of your producing height is induced on prop fractures, and that's somewhat in line with what they've seen at the UT and some of the studies they've done down there. I think the numbers were consistent with that. But that's one of the big variables right there. So we've got one data point here. We know we're not producing out of just the propped height. Your recovery factors get ridiculous if you do that. We also know we're not producing from the entire bench, but this gives us a better bench. Another thing that came out recently at the annual meeting, which was very interesting, they've got a new technique, a company called Biota out of San Diego, looks at the DNA on the vertical pilot going down and sees the signatures in the oil up and down the wellbore. And then when the well starts producing, you can see which fingerprints are coming out. And coincidentally, the Wolfcamp example, we're assuming, we don't have the logs on this, so we're assuming there were no stress barriers in there, but it came out about 210 feet, which matches our preconceived notion, so it's got to be right? At any rate, that's another data point, because this is something that's very hard to measure, but we feel pretty comfortable that using this works pretty well. Some equations, just some example equations, not to use. I mean, this is good for the Wolfcamp Shale, Wolfcamp in the Southern Midland Basin, but we've got about 8 or 9 different models depending on where you are in the Midland, Delaware Basin. So this is not the model to use for everywhere, and certainly not to use outside the Permian. But spectral gamma ray, you can see there, we've got a gamma ray conductivity and neutron input. Your normalization values, I skipped those up above for that particular area. The V-clay, we use multiple indicators there. I don't think just gamma ray by itself works very well. What you basically do is you train it to a certain value. You tell it to train to the ECS V-clay. You start with gamma ray, see what it looks like, or spectral gamma ray, see what the correlation coefficient is. Add a neutron, does it improve it? Sure, then keep adding curves. And go ahead and add a conductivity and see if that works. And then you don't want to put too many in there, but just enough to give you a decent correlation coefficient in the 70 to 80% range is what we typically like to see. Sometimes you can't get there, but it's better than nothing. I mean, better than not having this information. The SynPore is the important one. That's the one that takes out the kerogen. We use the normalized density, the spectral gamma ray, normalized neutron, conductivity again. We also have one with PE, but that doesn't really improve it that much, really. Poisson's ratio, you can see we do need PE there. We get a pretty good correlation coefficient with that, also with Young's modulus, and those are the numbers we use down there. Typically, those are pretty good. The other thing, too, from the rock properties is, at least in the Midland Basin and in Delaware Basin as well, most of your barriers there, most of your high-stress areas are the carbonates, or the tight carbonates. So even if you don't have a full-wave sonic and you don't have a correlated Poissons, the thick carbonate sections or multiple thin carbonate stringers that are low porosity typically are where you see the higher Poisson's ratio. So you can almost use those versus using a quantitative number from the analysis. There's an example raw log from Reagan County, Midland Basin. You see the unnormalized spectral gamma ray on the left here. Even in your good shales, you're going to have a spread there. So you have to multiply the spectral, usually by about a 1.5, 1.6, depending on the service company. But we've got that over here. You'll notice we've actually got the normalized values over here. They're a lot closer together here, and they actually come together where it's not radioactive. And then you're shading over here. PEF, neutron density, resistivity, and there's your outputs here. Basically your spectral gamma ray, total gamma ray, your lithology model. And again, we use the lithology model primarily for correlation. We don't use it in any of the calculations like some of the other UAN type models use. But again, that's the way we do it. Water saturation, stress, and then your effective porosity with your PEG calc over here to the right. Get this guy out of the way. Okay. I guess we already got the results from the survey on this, and it sounds like most people are using ARPs on this. But recovery factor is the next step. What do we do with the oil in place numbers? What's the next thing? Well, try to go look at what the recovery factor is. How much of that oil in place did you get out with certain assumptions that are made? We like recovery factor over some of the other methods. The discrete fracture network, the dual permeability, modeling with permeability, modeling with, trying to, and if you have microseismic and all that information, you can probably make it work a lot better. But trying to use a permeability-based model for performance in organic shales, there's a lot of issues. You probably do it, but if you can get around it, which I think we are with this, I would recommend that as another option. But you want to get your EUR, your ultimate hydrocarbon recovery, and that comes typically from decline curve analysis, 9 times out of 10, if not more. The different methods, in fact, there's a whole course that Shah Kabir offers. In fact, coincidentally, it's the week before our course coming up in February, so it's not a prerequisite for this course, but it's recommended that you look at that, or at least look at these methods. Various methods, most of them are, all of them except their ARPS are, are blessed in some condition or not. ARPS is not, but again, ARPS is what most everybody uses. It's what most of my clients use. So there's some ways to improve on that. One thing nice about some of these new methods is it's Drilling Info has upgraded their modules quite a bit to where they actually have all these, and they also include the Duong model in there as well. So you could try that and see how they look, because you want to spend some time getting this right. That's probably one of the weakest points in this, because you're typically working with relatively limited production times and fairly long producing periods overall to estimated ultimate recovery. So sometimes you're working with a little bit of data and you want to make sure the model is as accurate as possible. The other thing is rate transient analysis, which is actually part of some of the other models there. If you can get that to work. Gas wells P over Z, is good. If you can get the second P, the first Z is probably, first P is good, the second's usually harder. One thing that doesn't work very well is rate cums. You just don't have enough production time on these. But your oil in place, gas in place, you just tie all this together. Those are your equations down there, fairly well established within the industry. And then your recovery factors, we try to do it on an acre by acre basis. We do an EUR per acre, then we do an oil in place per acre number, and then that's your recovery factor. Concept's fairly simple. How much is coming out of how much you got in the ground, and then you're trying to establish the pore volume, the saturation, the height, and the oil in place down below in the reservoir. How much of that is coming out of the ground is really what the recovery factor is. Drainage area normalization depends on the area. This is for the Wolfcamp in the Midland Basin. Typically, I can say the historical Wolfcamp, operators are starting to experiment with more wells than 6. I've seen some people go to 8 in some areas. This one assumes 6 wells per 1.5 sections. You get 160 acres per well bore, and then you just basically try to allocate your oil in place and your EUR per acre to the number of acres based on a function of the length. Again, everybody's on fairly intense stage spacing now, where you don't have 500-foot stages out there anymore, where you're not sure how much you're actually draining. We're getting down to where you're pretty sure we're getting most of it. So, with the current practices. But again, this is for the Wolfcamp in the Permian. For instance, in the Bakken, we got for 2-section laterals 320 acres as your number out there, just based on the spacing, because they typically put 4 wells per pattern there. But anyway, that's a number. Is it an exact number based on drainage? It's a good question. It's right now it's a benchmark. It's something to be consistent with, and it is going to probably change when you start putting more wells in here in various areas. So it's going to be relative. But then again, it should be able to predict the same type of performance in the same type of situation going forward. So that's a good feature. Here's an example where we tie it all together. I guess it's out of Andrews County. You've got your basic curves over here we've talked about already, and then your key curves here. This is your stress curve from the dipole sonic correlation. Stress barriers down here. You probably could have moved that up just a little bit, but we've got a pretty strong barrier here, which notice coincidentally corresponds to a tight porosity streak. We're pretty sure that's all it's producing there, possibly up here, but more than likely down there. If you look at this interval here, take the oil in place from integrating the data here, you come up with a Gen 3, Gen 2 number, which we came up with around 11.3. You get 300,000 barrels, 304,000 barrels, and the EURs around 330. So we're not trying to get down to the third decimal point here, but historically we've been very successful in saying, yes, this is a good area, or no, this is not a good area. That's usually the first concern. Whether we get 300 or 350 or 250 or whatever, those numbers can move around a little bit because, again, we do have a lot of variables. And we're making constant changes to our model. We're always upgrading the quality of the model. So we're getting better and better as we go, and I think we'll get better and better as we do better methods of EUR calculation as well. But that's basically the concept. Is this economic? No, probably not. The stress barrier is what really ate the lunch here. If that stress barrier wasn't there, it probably would have made a difference here. You probably would have had an economic well with that. But that's kind of on the low end of what people are looking at right now. Most of the operators I'm looking at are, targeting wells at least 500,000 barrels or better on their wells, recoverable. And then this is oil recovery, not BOE. We typically work in just liquids. If you want BOE, you have to look at what your GOR is, etc. What we've seen historically, we did a paper back in 2015 annual meeting, which at 8.2 is what we had in the southern part of the Midland Basin, the study we did down there, and those were mostly Gen 1 fracs, 700, 800 pounds per foot of lateral. Gen 2s where we did a lot more of the work since then. We're coming up with a fairly consistent number here as well, which is kind of interesting. I did not expect this degree of consistency, but it does. Gen 3, we're still working on that. We're starting to get some producing times that are reasonable right now from the larger jobs, and we're right in the middle of looking at about a dozen of them right now around the basin. I haven't pulled all that together yet, but what we did initially was looked at the EUR studies that were done that showed how much increase in EUR are you getting between the generations, between the 1,200 to 1,500 pound per foot, which is what your Gen 2 is, and your 2,000 pound plus. And we think it's about 27% higher, and that gives you about a 14.3. And the initial numbers we're getting off the comparisons are in that ballpark. We haven't got enough to be able to statistically put it out yet, but we will have that shortly, definitely by the school. But anyway, that's where we are there. And this is the EUR trends we looked at, basically going from Gen 2 to Gen 3, around 27% increase. But and that gives you around 14. That could be higher, could be lower. That's a number that's still a moving target, but it's a good ballpark. It's definitely better than 11, and it's definitely increasing though. So that's an important number. So we think the overall process gives you an effective means to forecast well performance in organic shale reservoirs, and using just a conventional triple combo is what we like. It requires a calibrated petrophysical model. You need to integrate the rock properties to get your producing height so you know what's producing. You have to assume the drainage layer area from lateral length, and then correlate back to good EUR data. And then what's nice about it is once you get a range of recovery factors, you can start using it to forward model your performance in the area to come up with what your reserves are going to be. And then, like we said earlier, the beauty of it is it doesn't require direct offset production in the area once the model is calibrated for the area. We've done production out in a lot of different areas that are way removed from existing production, and then when they've gone back in to develop the areas, the numbers come out looking pretty good. Okay. The course detail, Susan mentioned a little bit about it earlier. Again, 19th and 20th, 19th and 20th, I think it is 2018. It's a 2-day course, not 3-day. I think it's the 20th. One thing about the course is the second day in the afternoon, we've got a little bit of time there to cover individual cases. We encourage students to bring their own LAS files, core data, specialty log data, ECS, XRD, and offset production analysis, and just the production. We can do the analysis in the course. We'll develop equations in the course, basically through my power log model. We don't have to have a power log model on your computer to do it. We'll generate equations for the course, develop a workflow for your area, and then something you can take back. So it's kind of a good technology transfer method. We also have a complete petrophysical analysis package, a spreadsheet in there to calculate raw numbers on a point-by-point basis, and we also have some ARPs. We have an ARP spreadsheet we use. We're working on trying to get some of the other ones going, but again, with the drilling info availability of all these, and the majority of people have drilling info now, so it's you may not need to develop that. So we're probably not going to develop the Excel routines for the other models, but again, you don't need a power log license to attend. We'll provide you with equations and workflows. That's about it. I'll turn it back to Susan.
Great, thanks, Bob. So I want to remind our listeners that you can't ask your questions out loud, but you can certainly type them into the question form in the webinar. After today's webinar, you will receive a link to the recording of this webinar if you want to share it with your colleagues. An evaluation form, we welcome your feedback, and the link to registration details for Bob's course. We certainly are learning a lot from this webinar series. I know in some cases people are saying they put the recordings on their playlist so they can listen to them while they work out or commute. So we're hoping to get some questions. I think they're starting to come in now. Let me see if I can pull up some of these so we can review them. So our question is, your examples and experience appear to be mostly oil, but you mentioned making some models in the Marcellus. Can you comment on this workflow or the petrophysical model for recovery factor of highly mature gas shales? Some of these yield EURs from decline curve that exceed gas in place determination from petrophysics, even with calibration to core, normalization, etc. So talk about your experience in the Marcellus.
That's good. That's a good question, because one thing we don't consider in our liquids analysis is the sorbed gas component. What are you going to get from the actual gas that's absorbed to the kerogen, which is not going to be part of your pore space. It's not going to be part of your pore volume. You're going to get quite a bit. And the project we worked on up there, I didn't get involved directly in the calculation of it, but I think the number we came up with was somewhere around a third of the overall gas that was going to be produced was not from the pore volume. It was going to be from the absorbed gas. So you need to know your Langmuir constant. You need to know your numbers. Your TOC is very important there. The gas wells, you actually can do a little bit better job of defining TOC there, because your total organic carbon in a gas well is all kerogen. So you can actually take a stab at making some estimate of how much kerogen is in the rock from that. So that's the beauty of that particular type of rock, where you don't have to worry about the S1, S2 difference. You can use the number as your kerogen. And it's not, TOC is not kerogen. You have to convert it. But the conversion is a lot simpler when you don't have to worry about how much of that TOC is S1 and how much is S2. But we did that work early on, and to be honest, really haven't done a lot of work up there since then. And although it's fairly straightforward, the petrophysical model is very straightforward. We've calculated the raw inputs a lot, but haven't done a lot of correlations in the Marcellus to see what type of recovery factors we're seeing. But it's probably a simpler reservoir to analyze than the liquids-rich ones. But we haven't done that much there.
Great, thank you. Bob, a lot of your work depends on having data, having core data, having triple combo, all the best log data. What sort of data collection method do you recommend, particularly in a cost-constrained environment? Good
question. What's nice is that we've developed these models early on in a couple of big projects we did in the Midland Basin, and developed the equations. And then as we got access to other wells within the basin for a pretty broad area, we were able to use the same equations and got a pretty good match. Like Northern Midland Basin, Central Midland Basin, the equations we developed right at the very beginning of this project, we're still using them because they still match. You start getting into different areas like the far south where it's a little softer, it's a little harder to get, use the northern numbers, and Delaware Basin is a little bit different. But yeah, you got to have data somewhere. There's a lot of data out there, a lot of public data. We've seen ECS data publicly released. Those of you that are involved in the Core Lab Symposium have got a wealth of data there, and all these. I recommend those participate in those type of consortiums if you want to get up to speed fairly. Now they're fairly pricey, but again, so are the wells. So, the cost relative to the cost of the wells is probably fairly minimal. When you're looking at spending $6 million per well after you've already spent $30,000 an acre for this stuff, it's buying additional data or buying into consortiums is probably not a major percentage of your overall budget. So that's something that's always there, and they've got pretty good coverage. We've seen their data pretty much all over, and where operators have had this and we've had the access to look at it, it's matched our models pretty well consistently.
Great. Our next question from a listener: how are the core processes used for calibrating log interpretation, and how is that measured?
Good question. We primarily like to use the GRI method. Conventional analysis doesn't seem to work too well on these organics. You typically get much lower porosities than what you would see. But GRI seems to be working fairly well with all its limitations. And again, that's one area we are working on to refine a little bit more. Typically, like I said, we use the core as our maximum. If you got fairly low V clays, then your maximum is your core. The closer your core porosity is to your effective porosity, that's how you scale your calibration. As you get down to some of the lower members of the Wolfcamp, for instance, where you got a lot more clay content, you expect to see a spread between the core porosity and your effective porosity. And we haven't quantified that, but we give a little more spread in the shales, in the shalier sections with more shale than we do in the organic section. Some of the organic sections with high gamma ray have very little clay. So there your core porosity is equal to your effective porosity. But we can't, and we need to do a little more work on that to quantify that a little bit better, but I think it'll give us a little better answer. But that's it. It's definitely a maximum to what we get, but and it should be higher than the effective porosity, and a little more higher than in the shales than it is in the cleaner zones.
So the next question from a listener, logs in laterals are pretty rare and mainly from pilot wells. Can you comment on how to scale up information from vertical data?
I haven't done too much as far as trying to do the recovery factor analysis using the logs in the lateral. I'm not sure I completely understand the question. It's most of the data we use is from the vertical wells. The lateral analysis was more for, most people are running it primarily to try and do engineered completions, which, I don't discourage those. I think people have good results in those in the past, but one cloud that's kind of come on the horizon with the engineered completions is these intrastage diversion techniques people are using, where you're going with a lot of clusters and a lot of diverter, and you're trying to force the frac to open up all the clusters, whereas in the past the engineered completions were trying to find the like rock. So I think the trend towards the intrastage diversion might cut that trend back a little bit of trying to do the analysis in the laterals, to try and space the perfs based on where the rock is similar. Because I think right now what we're seeing in the best Gen 3 results are with the higher number of clusters per stage and with the shorter stage spacing, which basically if you're going to put 10 clusters in a 150-foot section, you really can't really engineer that very well, but you'd have to use some kind of diverter with that. So I think some of the trends in the industry are getting away from getting information in the laterals, not to discourage getting it. I think it's great to show you your heterogeneity of the rock and all that, but just putting 2 or 3 clusters in a stage just where the rock's the same versus putting a bunch of them to try and get a lot of near wellbore stimulation. I think the trend is towards near wellbore stimulation with a lot of proppant per foot of a lateral within fairly close stages. And what it also does is it doesn't you minimize your frac hits with that, because you tend to get more near wellbore, and you also minimize your height. So I think you're seeing a lot better results from these really intense near wellbore treatments, that if you start getting too fancy with your perf selection and start getting out there and limiting the number of perfs per stage with the good stuff, you may get a lot longer. You really don't want long fracs right now. The long conductive fracs are not the goal in shales right now. You want a lot of short conductive fracs around the wellbore with a lot of complexity. So that trend, I think, may slow down as far as getting a lot of information in the laterals because of that.
Great. So our next question is, recovery factor estimation as presented assumes uniformity in traverse direction to a horizontal well axis. Is this provable?
That's a good point. You're always going to have heterogeneity out there. One area we've run into that is over in Howard County, for instance. We typically always underpredict. I mean, across the board, we'll always have several outliers in that area that are like, whoa, And what happens there is you start getting into you hit the Wolfcamp debris flows, which are nice, clean carbonates that sometimes can make 1 million barrels on vertical wells up there. We've seen some when I was logging for Schlumberger out there that little acid jobs will make 1 million barrels. You hit one of those, your numbers are going to be off. Within the basin, you can look at your logs from well to well. Typically, when we do a recovery factor study, we try to get it probably 2 to 3 wells surrounding the well that was completed, so we can see if it's homogeneous between at least the log response around the producing well is consistent. Do a cross section through there, and basically we do the rock properties in one place for, say, all 3 wells surrounding it, and maybe take an average if you're not right there at the pilot well. So we try to address that with well control. If you've just got 1 well and your lateral's a certain distance away, you're right, that is an issue, because you need to have some kind of geology. Ideally, what we do on these, in the large projects we've done, about a half a dozen very large projects, is you basically map the parameters. You map the parameters from your well control, map your porosity, map your saturation, map your net pay, and use that to forecast your properties for the intra-well numbers, instead of just trying to use 8-inch wellbore 2 miles away. Use a number of 8-inch wellbores spaced around the area of study so you can go ahead and map that. I think mapping is important. And sometimes the mapping, too, on a point we didn't really talk about, is the weakest measurement on the logs is probably the water saturation. We've seen, a variety of different numbers. We'll map the water saturation on some of these. You'll have 3 wells that have very similar water saturation, all of a sudden you have an outlier. And sometimes it's because they ran the wrong tool, where they ran an induction salt mud or real fresh mud. But more often than not, it's not, and you almost just have to normalize the saturation based on the mapping. So it is an issue, but again, hopefully with multiple wells and mapping, you can get around that to some degree. But it is a good point, and these are a lot more homogeneous than, say, fluvial reservoirs, for instance. You're able to book reserves, reserves on these fair distance away from your control well, so it's more homogeneous. But again, there is heterogeneity, which is a good point. It does come in.
So the next question is related to the poll that we conducted on the method that companies are using to estimate EURs. Just to remind everyone, we had 36% responded ARPS. We had 2% on the Valco method, the stretch exponential. We had 0% on ILK, the power law, 2% on logistic growth, the Clark method, and 64% said other. Can you comment on those results?
It's kind of what as far as the other goes, I'm not really sure what the other may be just using a reservoir engineering firm or using a third party, or sometimes what we'll do on these when we first started out is we'll just get the operator to give us their numbers, and we don't really know where they came from. But most of the operators I work with do use ARPS. It's, again, with all its limitations. The other ones have got a lot of features that are good, but I think that's something you're going to see change, and particularly with Drilling Info, their new version, adding all these routines in there where people that have Drilling Info can do that. Not to plug Drilling Info, but they've got all these methods in there which typically weren't available in the past, and where people were using ARPS. But it's definitely one of the weaker points. I think we need to put more effort into some of these more sophisticated models that address the true nature of the flow regimes and not just an empirical model, which is what. ARPS is a 1945 empirical model, so things have changed a little bit since then, and the type of reservoirs that we're developing. But again, that's where we're at on that situation.
So the next question is that it's commonly said that 80% of the production comes from 30% of the perfs or stages. Can you comment on this, please?
In the past, you've seen the production logs. There's several papers. I think Schlumberger had a 200 well study they did. Most of the production log studies I've seen, though, were back during Gen 1s. We had 300 to 400 foot spacing on some of your stages, 5 clusters, 4 clusters, 5 clusters. And the Gen 3 fracs now are going with, a lot of clusters, 15 to 20 foot spacings over 150 to 200 foot. I'm not sure you're going to have those same problems there, particularly if you use intra-stage diversion. Or engineered completions. It's documented that using engineered completions helps. The Eagle Ford, there was a big consortium down there that came up with that showed you got something like a 30% or more increase in your production from doing the engineered completions. I expect you're going to see similar results from these diverter, intra-stage diverter jobs where you're trying to force it to complete everything. The limited entry models have been revised. I think everybody's kind of realized that we haven't been putting enough delta P across the perfs on a lot of these. I think you're going to see a lot fewer perfs on different wells. You don't really need 6 shots per foot over 2 feet. Just a few 0 degree or 180 degrees fine. And you're going to see that done more and more. But I'm not sure it's still a problem with the tight spacing that we're going to. On the very long spacing wells, I think that was more of a problem then. I'm sure it's still an issue. If you go in and just don't do any kind of diversion or don't try to do any limited entry, I think you're going to see a large percentage coming out of a fair small percentage of your perfs. But I think the way the completions are trending right now, it's going to be less and less of a problem, particularly if you use the intra-stage diversion techniques.
Okay. So I'm going to give our listeners one last chance to ask a question. We've gone through several of our listeners' questions today. I want to remind you that you'll receive a link to the recording of today's webinar that you can share with your colleagues. You'll receive an evaluation form, a link to registration details for Bob's class on integrating petrophysics with rock properties and production data to predict organic shale well performance. That's scheduled for February in Houston. And thanks very much for participating in today's webinar. Goodbye.
Thank you.